We are now ready to define what is called the definite integral. So in this section, we're going to take the sum that we had out of our last section where we were examining the area under a curve. And we had derived a sum that we're seeing right here at the top of the page, this limit of the sum from I equals 1 to n of f of x sub I star delta x. Now, if we can just do a quick little recall on where that came from, that is coming from looking at the area under a curve and to approximate it using rectangles where we pick. So if we want to find the area under this curve from A to B, this is coming out of our last section. This is y equals f of x. On the interval from A to B, what we did was we said we first approximated it by the sum of a bunch of rectangles, n rectangles. But then we said if we let the number of rectangles go to infinity of that sum, and on each, I'm going to just draw 4 rectangles, and just for the sake of time and the video, oh, actually, I'm going to draw 5 because that's the way my graph worked out. So I'll use n equals 5 in this case. And I use the right-hand endpoints. So notice on this particular one, that was just the way it worked out, the way I quickly drew that graph. But we're going to let those shrink down anyway. We're going to let n go to infinity. But the height of these rectangles, we find by looking at a tag somewhere in the subinterval. We call it x sub I star. That is what we call the tag on the subinterval. It can be a right-hand endpoint as I've drawn here. It could be a left-hand endpoint. It could be a midpoint. It could be any point in the subinterval. So this is a tag on the ith interval. And we use that point to give us the height. So as I drew here, I'm using right-hand endpoints. These rectangles, I was using the right-hand endpoints to generate the right-hand endpoints of each interval to generate the height. So this represents the height of each rectangle. And delta x represents the width of each rectangle. And the width of the rectangles, by the way, we could have mentioned this up here. The width of the rectangles, delta x, each of these widths is delta x. And delta x is always found by taking b minus a, the length of the interval, and dividing by the number of divisions. So that's the length of the interval divided by the number of divisions. N represents the number of divisions. Okay, so this is the sum of n rectangles areas. And remember, rectangles are always height times width. That's how we calculate the area of a rectangle. So we take n rectangles, we add them up, so this goes from I equals 1 to n, and then we let n go to infinity. So it's a quick review of where we're coming into this section with. We did this in the last section. We did a lot of estimation in the last section where we picked an actual finite value for n, and we calculated areas using rectangles and, n's equal to, say, 4 or 6 or 10. Right? But of course we want to make this more accurate. We want to find not an approximation, we want to find what our area is actually equal to. And so we had come up with this expression for n, the sum of n rectangles, and then letting that limit go to infinity. Well, that comes up so much in calculus and so much as we try to find areas, and even when we get into volumes and more physical applications. For instance, the work that it takes to do a task, this physics concept of work and volumes and surface areas. We have this idea that we break things into smaller pieces that are manageable for us, like areas of rectangles. And then we take those and add up all of those smaller pieces. And then to make it more accurate, we let the number of divisions that we're making go to infinity, and that creates this limit. It's this process called finding Riemann sums, actually, after a German mathematician. But here, let's focus in on this specific definition. It says that this is the definite integral, and it says given a continuous function, it turns out actually we can have a finite number of discontinuities, but we won't get into all those nitpicky details here. So let's say given a continuous function, y equals f of x on an interval, we will divide up the interval, as I mentioned. So here's our delta x definition into b minus a over n. Delta x is b minus a over n. And then we make a set of endpoints, or sometimes they're referred to grid points, depends on the textbook or the professor that you're talking to. So we will divide each of the subintervals, we'll divide up the entire interval into a bunch of smaller subintervals, each with endpoints x0, x1, x2, x sub n. And then each of the subintervals, if we look at a generic subinterval, we would write it as x sub I minus 1, x sub I. Pick a tag somewhere on that subinterval. It can be equal to the right-hand endpoint, the left-hand endpoint, the midpoint. It can be anything in that subinterval. And then use that point to calculate the heights of your rectangles. And those give you the f of x sub I star. And the delta x is the width. So here again is height times width. So here's our height times our width of our rectangles. Height and width right there. And that turns out, when we take the limit as n goes to infinity, we will now define that to be the definite integral. So here's our new definition. That is the definite integral. So we're taking something that we've already worked with and we're giving it a name. We're calling it the definite integral of a function. I'm going to highlight this whole piece right here. And we'll reference this a lot in this section. We will utilize this a lot in this section. And so this symbol looks sort of like an elongated S. That is an integral symbol. I'm going to go through the notation a little further on in this slide. So that is the integral. That is the integral. That symbol is an integral. These bounds, these limits called limits of integration, A and B, are telling me the interval on which we're looking at it. And then what is the function and what are we integrating with respect to? So we've got all kinds of little new notation to work with here, but it is really giving a name to that area that we've already defined. Okay? Quick note, if we choose our tag to be the right-hand endpoints, then on each interval, remember that the interval x sub I minus 1, x sub I, and that's what each subinterval looks like. And so x sub I star is a tag that comes from that interval. So if we were to choose the right-hand endpoints, this is the right endpoint of each subinterval. If we were to choose the right-hand endpoints, then our tag would be just x sub I. So the integral would be equal to the integral from a to b of f of x dx would actually be equal to that limit of that sum of f of x sub I. This, by the way, in the subinterval is the left-hand endpoint in our notation, x sub I minus 1. So using the left-hand endpoints, this tag would be just, rather than writing x sub I star, it would be x sub I minus 1. And the midpoint, x sub I bar, is how we denote the midpoint. And the reason it has that bar is because it's actually an average of the two endpoints. The midpoint, by its definition, is x sub I minus 1 plus x sub I over 2. It's the average of the two endpoints. That's how you get a midpoint. Oh, I actually have that right there. X sub I, wrote that wrong. X sub I minus x sub I minus 1. Over 2, it is the average of those two. Okay, so that's where we're getting those definitions. Notice there the tag has been plopped right in there. Okay, so now let's go ahead and, just a couple more little notes. I was going to go ahead and jump into my example, but before I do have a couple more notes that I want to mention here. One is what I mentioned earlier. We specified that the function needed to actually be continuous, but it turns out that this integral and this limit definition of the sum, the limit of the sum, turns out that we could actually have a finite number of removable or jump continuities, and we can still integrate it. Now, it goes a little beyond the scope of this course, but I always like to mention that here, that it is true actually that this definition of the integral expands beyond just continuous functions. Okay, the summation that we're looking at is called a Riemann sum. So this is a Riemann sum, and we will refer to it as such from here on out. So when you hear a Riemann sum, you'll know that that is a sum from I equals 1. It's a sum of n terms, f of x sub I star times delta x. So a Riemann sum. Now, in terms of just some symbols and some definitions, A and B are what we call the limits of integration. A being the lower limit of integration, B being the upper limit of integration. They are placed on the integral symbol, the symbol itself, integral from A to B, of f of x, the function that we're integrating, dx, and that is actually the differential. Dx is called the differential. So that is just some notation and some new language for us to get comfortable with. And one more piece. We have not specified that f of x has to be positive. Now, when f of x is positive, the sums, the rectangles in our Riemann sum, all have positive area. But it turns out, actually, and we'll explore this a little further after we've done a few examples, it turns out that the integral of f of x dx, which is equal to, again, let's just rewrite our definition of our definite integral here, I equals 1 to n as n goes to infinity of f of x sub I star times delta x. And this turns out is actually equal to what we think of as the net area between, because of the way f of x as heights of rectangles, if the function itself goes below the x-axis, the rectangles, as you can see on this graph on the left here, you can see those rectangles right in here going negative heights, right? The f of x values are negative, so those rectangles, by definition, when we set them up and use them in this Riemann sum, they actually drop below the x-axis, creating negative, if you want to, areas of those rectangles. And so when we add it all up, what we get is this net area, this balance between positive and negative area. So it's the net area between the function, the curve, y equals f of x, and the x-axis. And so it's kind of fun. We'll explore it a little bit. Turns out, I'm going to highlight that word net area. It becomes the net area. If, of course, the function is all positive, then it's a positive area. But turns out, actually, that integrals, definite integrals, can be either positive or negative. And what they represent is the net area trapped between the function and the x-axis. Okay, so it's the net area between the curve and the x-axis, where area that falls when the function falls below the x-axis, we're actually getting, in a sense, a negative area. Okay, so we'll get back to the graphical visuals here in a minute, but let's do a couple of these definite integrals. Let's actually use our definition. Let's set up a couple of definite integrals and actually compute them. We'll need some sum rules in order to do the computation, because calculating the limit of that sum can get a little bit complicated, and we'll need a little bit of a little more tools as we do that. But let's start with set up the definite integral, and we'll talk about the computation after we've got it set up. So I have this function, and I want to integrate it from 0 to 1, 3x squared plus x dx. Now, doing that, I'll keep in mind what that means is to find, this is always kind of keep bringing us back to to what we're doing, what the context is of this, and after we've done some of the setup and the computation, we can revisit what it means graphically. So let's just say this. This means, when I say that, find the area. I'm going to say net area since we've just talked about it. Find the net area between y equals 3x squared plus x. I actually think this is always a positive function on the interval we're looking at it, but we're saying net area between y equals 3x squared plus x and the x-axis. So that's what we're doing. We're going to get into computation, but it's good to remember what we're doing. And so the definite integral is the limit as n goes to infinity f of x sub I star times delta x. And what we need to do now is figure out, we know what f of x is, but we need to figure out what the tag is, what the delta x is, and we need to plug those in. So let's talk about it. So delta x is the width of each subinterval. And it's defined to be b minus a over n. Well, a and b are given as 0 and 1. So delta x is 1 over n. X sub I star is the tag. Now, I didn't specify what we had to use for the tag. A lot of times the specification is given. So let's go ahead and just say, let's use, I will add it to the instruction. So f of x equals 3x squared plus x on 0 to 1. Let's use right endpoints. Okay, we could do the same calculation with midpoints, left-hand endpoints, but let's go ahead and use right endpoints. So if we use right endpoints, remember that x sub I star, this is what I just wrote a minute ago, is in the subinterval from x sub I minus 1 to x sub I. And if we're going to choose the right-hand endpoints, that means that my tag is actually going to be x sub I. Okay? So my tag is going to be x sub I. So let's think about what x sub I would actually look like. If I'm going from 0 to 1, I'm dividing the interval up into n subintervals. X sub naught is 0, the starting place. x1, x2, x3, and so forth till I get to x sub I minus 1, x sub I. And let's scooch that out just a little bit further. Let's make one out here. And x sub n is going to be 1 by the time we get all the way out to 1. So we're focused in on this little subinterval right here. Now, each of these widths we've already talked about. It's 1 over n. So each of these widths is 1 over n. So if each of those widths is 1 over n, I have to move down below because I need a little bit of space. X sub naught is equal to 0. X sub 1 is going to be 0 plus 1 over n, which is, of course, just 1 over n. And then x sub 2 would be 1 over n, because we're going to go from x1 to x2, plus another 1 over n. So it's going to be 2 over n. And x sub 3 is going to be 3 over n, because from 0, we would go 3. We would need to add 3 1 over n's. So we would have 0. I guess another way to write that would be to say 0 plus 2 times 1 over n. And that, of course, is just 2 over n. And x sub 3, I'm saying it, but let's write it down too, is 0 plus 3 times 1 over n. So it would be 3 over n. So by the time we get to x sub I, which is the tag that we're trying to figure out how to represent, x sub I is going to have to be 0 plus, we've gone I of those little delta x's. So I times 1 over n. So x sub I is actually I over n. So x sub I is equal to I over n. Okay. All right. So now we have everything we need. We know delta x, we know what our tag is, and we know what our function is. So let's set this up. So let's go back to our integral. And our integral now, I'm going to just come right back up here. We have the work down below. Our integral is equal to the limit as n goes to infinity of the sum of f of I over, remember, x sub I star is equal to x sub I, which is I over n. So it's going to be I over n times delta x, which was 1 over n. Now this is from I equals 1 to n. So we are almost there. Now we're going to use the function and plug in I over n. So I'm going to come right here. I'm actually going to come down below my work so I have a little more space. Grab this and bring it down. Our integral from 0 to 1 of 3x squared plus x dx is equal to the limit as n goes to infinity of, now I'm going to plug into this function. So the sum from I equals 1 to n of 3 times I over n squared plus I over n times 1 over n. And I'm going to simplify that a little bit. This is the limit as n goes to infinity of the sum from I equals 1 to n of 3I squared over n squared plus I over n. And we have this 1 over n here as well. I'm going to go ahead and distribute that 1 over n in, so that becomes n squared, and this actually becomes n cubed. Okay, so we have simplified this at this point. We've gotten this nice and simplified into this compact sum. But I want to actually get to an answer. I want to know, what is this area? So that's where I have to rely a little bit on some pre-calculus skills and some summation rules. And you can look in the appendix of our book at where these summation rules come from. I'm going to go ahead and project them. They're useful rules when we're computing Riemann sums. And so I'm going to project them right now so that we have them, and then we'll use them to solve this actual integral and find this area. So here are our summation rules. So our summation rules say that if we're summing, and I won't go through all of them, but if we're summing, what I want to focus on is this one and this one, because we're utilizing those right now. It says that if we're summing up the integers from 1 to n of I, that answer is actually n times n plus 1 over 2, and that can be proven just using a little bit of algebra. It's kind of a nice little proof, so you can check that out. And it says if we're summing the integers from I equals 1 to n of I squared, that we get n times n plus 1 times 2n plus 1 over 6. So those summations up to n, can actually be replaced with these expressions. We even have an I cubed one here as well. Also, if we're summing terms that we're adding or subtracting, we can look at the individual sums. And if we have a constant, we can pull the constant out to the front. Okay, that's what our sum rules are. And you can reference these sum rules as we're doing these. You don't have to memorize these. You can reference them. But make sure you know where these references are. So take a pause of the screen and write these down, or know where to reference them in the textbook. Okay, so let's head back here, because what I see here that I want to utilize those sum rules for are that I squared and that I. So I'm going to break this down, and let's see if I can keep those sum rules on the screen kind of with us as we go. And you can watch me apply those sum rules to our summation here. So this is actually going to be equal to the limit as n goes to infinity. What I'm going to do is I'm going to split that sum up using the rule that says that I can break this up. I'm going to write this as 3, I keep wanting to write infinity on the top. It's a little preview of some Calc 2 stuff there. So sum from I equals 1 to n of 3n cubed times I squared. Okay, so I'm going to write it like that, plus the sum from I equals 1 to n of 1 over n squared times I. And then what I can do, excuse me, is I can actually take the sum of I squared and I right from my sum rules over here, because the sum of I equals 1 to n of I is n times n plus 1 over 2. So this is actually just equal to the limit as n goes to infinity of 3n cubed times, and I squared is n times n plus 1 times 2n plus 1 all over 6, plus 1 over n squared, and then the sum of I. When I add up I from 1 to n, I get n times n plus 1 over 2. Okay, so I'm using sum rules, using my sum rules. Right here is my box. And let's go ahead and zoom in, because now I actually am at a place where I can use my knowledge of limits to continue and simplify this down. So I used my sum rule. So right here I was using my sum rules to replace the I squared and the I. All right, so this is now the limit as n goes to infinity of 3 over, oh, you know what, let's get a little bit of simplification here. The 3 and the 6 will reduce. I'm going to expand that out in the top, so I get n squared plus, actually, I'm not going to expand it out. I'm going to simplify one of those n's, and one of those n's cancels there. So I have n squared there, and then I'm going to expand the top, 2n squared plus, that's going to be 3n plus 1. Plus, I'm going to do the same thing here. I'm going to reduce that n with that one of those n's there, and I get n plus 1 over 2n. And let's keep going, simplify, because we're trying to take this limit as n goes to infinity. This is now 2n squared plus 3n plus 1 over 2n squared plus n plus 1 over 2n. Single terms, I'm going to divide at limit as n goes to infinity. I'm going to take this limit, but before I do, plus we get 1/2. And now I can take the limit, and the limit of each of these as n goes to infinity, each of these terms that has an n in the denominator and a constant in the top goes to 0, and I get 1 plus 1/2, which gives me 3/2. Now we have an answer, and it took us a little bit to get there because we first had to set up the integral. We had to set up the integral as a Riemann sum. Then we had to evaluate that Riemann sum using the sum rules, and then we had to take a limit. So kind of just to walk us through our process, I'm going to write those out. So we had to set up the integral as a Riemann sum. Then we had to simplify the sum, apply sum rules, and I will say here, when applicable, sometimes we're just not going to have the sum rules so that we can calculate these, and we're going to have other ways to do that, but I will say here, when applicable, and then take the limit. So that was our process here. But we've got an answer here, and I just want to remind us what that means, what that answer means, and that goes actually back up even higher. What that integral means is actually giving us the net area between y equals 3, x squared plus x, and the x-axis. It's actually giving us an area between the curve and the x-axis, a net area, but it is giving us an area.